Hello everyone, welcome to Neso Academy. Till now we have implemented the half adder using behavioral modeling and structural modeling. In behavioral modeling, we described the behavior of the half adder using if-else-if statements, and in structural modeling, we created separate source files for XOR gate and for AND gate, and then combine them together using component declaration and port mapping to create the half adder. And today we will implement the same circuit of half adder using the third and the last modeling style, data flow modeling. Now, among all three modeling styles, data flow modeling is often considered the easiest for combinational circuits because it directly describes the relationship between inputs and outputs using Boolean expressions. So today, we will implement the half adder using data flow modeling in Vivado. Now, before implementing it in Vivado, let us quickly revise the circuit of half adder. Now, we have already seen that the half adder is an adder that adds two single-bit binary inputs and generates two outputs, sum and carry, without considering the previous input carry. And we can verify in the truth table that sum is high when A is 0 and B is 1, or when A is 1 and B is 0, which means sum is equal to A complement and B, or A and B complement, which means sum is equal to A XOR B. And here in the logic diagram, we can clearly see sum is equal to A XOR B. Now for the output carry, it is very simple. Here we can see that carry is high when both inputs are equal to 1, which means carry is equal to A and B. And in the logic diagram, we can clearly see that carry is equal to A and B that we have already constructed. Now, let's implement this half adder in Vivado using data flow modeling. Now, I hope you remember that what is data flow modeling and why we are calling this modeling style as data flow. Because in data flow modeling, we can clearly see the flow of data from inputs to the outputs via the logic gates, and it is clearly visible in Boolean expressions as well. Therefore, we are calling this modeling style as data flow modeling. Now, let's implement the half adder circuit in Vivado using data flow modeling. So, we are in Vivado and this is our VHDL code editor. In this, we are writing the VHDL code for the half adder. Here you can see that the code starts with IEEE library along with the standard logic package from the IEEE library. Now, why we are using this standard logic package? Because we want to use standard logic data type in this VHDL code. Now, after library declaration, we have our entity block, starting with the keyword entity, and here I have named this entity as half_adder because we are implementing the half adder circuit. Is port. Now, inside this entity, we will declare the input and output ports for the half adder. For that, I have declared A and B as input ports and sum and carry as output ports. And both inputs and outputs are of standard logic data type. Now, after port declaration, we can end this entity using the keyword end with the name of the entity half_adder. So, we are done with the entity declaration. After entity declaration, we have our architecture block. And here I have named this architecture as data flow because we are implementing the half adder circuit using data flow modeling style of entity name half_adder is. Now here you can see that the architecture is incomplete. Let me complete this architecture using Dataflow modeling style. Now in Dataflow modeling, we do not use if-else-if statements like we did in behavioral modeling. And we also do not create separate components like XOR gate and AND gate and then combine them together like we did in structural modeling. Instead, in Dataflow modeling, we will directly write the Boolean expressions for this half adder. Now, what were the Boolean expressions of the half adder? The output sum is equal to A XOR B and the output carry is equal to A and B. So, I will directly write these two Boolean expressions inside this architecture after the keyword begin. So, let me write these two Boolean expressions. So, here I will write output sum is assigned input A XOR input B semicolon to end the statement. Similarly, I will write output carry is assigned input A and input B semicolon to end the statement. So, I hope you understand why Dataflow modeling is very easy to implement because we just need to write these Boolean expressions using logical operators just like we did here. Here we use XOR operator and AND operator. So, I hope you understand the complete Dataflow modeling style code for the half adder. Now, let's see the schematic diagram generated by Vivado for Dataflow modeling style. For that, go to RTL analysis, select Open Elaborated Design and click on Schematic. First, let me save this file. So, this is our schematic diagram generated by Vivado for Dataflow modeling. Here we can clearly see the two inputs A and B that we want to add and the two outputs sum and carry. Here we have two logic gates, one XOR gate and one AND gate. And here inputs A and B are directly connected with the inputs of the XOR gate and with the inputs of the AND gate. The XOR gate generates the output sum and the AND gate generates the output carry. Now, I hope you notice that in behavioral modeling, Vivado generated comparators and multiplexers to describe the if-else-if statements. And in structural modeling, we created separate modules for XOR gate and AND gate and then connected them together. But for Dataflow modeling, Vivado directly converts the Boolean expressions using logical operators into the schematic diagram with the help of logic gates. So, I hope you understand this schematic diagram generated by Vivado for Dataflow modeling. Now, let's verify our code using simulation waveforms. For that, go to Simulation, click on Run Simulation and select Run Behavioral Simulation. So, this is our simulation waveform window. Here we can clearly see the two inputs A and B and the two outputs sum and carry. Now, the simulation process will remain same as what we have performed in the previous two lectures. So, to verify the VHDL code, I will quickly assign all four input combinations for the two inputs A and B and we will see the waveforms. First, let me assign the first input combination 0, 0. For that, right-click on signal A, select force constant, select value radix as binary because we want a binary value. Then assign a force value 0, then click on OK. Similarly, to assign signal B as input 0, right-click on signal B, select force constant, change value radix to binary and assign a force value 0, then click on OK. Now to run this input combination, let me run this simulation for 100 nanoseconds. For that, click on Run for 100 nanoseconds. Similarly, you can assign all three input combinations as well. Let me quickly assign them. So, I have assigned all four input combinations and generated the waveform. Let me maximize this waveform. Now, here we can clearly see for the first input combination, when both inputs A and B are equal to 0, sum is 0 and carry is 0. Let me move my cursor at this point. Now, in the second combination, when input A is equal to 0 and input B is equal to 1, then we are getting sum as 1 and carry as 0. In the third combination, when A is equal to 1 and B is equal to 0, sum is 1 and carry is 0. And in the fourth combination, when both inputs A and B are equal to 1, in that case we are getting sum as 0 and carry as 1, which means our code is absolutely correct. And I hope you understand why we use data flow modeling over all three modeling styles for combinational circuits, because it is very easy to implement. So, we are done with the implementation of half adder using data flow modeling in Vivado. With that, we are done with the implementation of all three modeling styles. So, we are done with this lecture, and in the next lecture, we will implement a new combinational circuit. So, thank you.